This is a lecture about chemical bonding and about the naming of, which is called nomenclature, of the compounds that are formed by the different types of chemical bonds. First thing you should understand is what is a chemical bond. And a chemical bond is simply two atoms that are so strongly attracted to each other that we think of them as joined together. And the type of attraction in a chemical bond is an electrostatic attraction. And specifically, it's an attraction between the electrons of one atom. So I'm just going to draw an imaginary ring. Of course, inside we have a nucleus, which has a positive charge from the protons. And so when you have two atoms that for various reasons are attracted to one another strongly enough, they will become bonded. And so the electrostatic attraction, again, is between the electrons of one atom and the protons of another. Okay, opposites attract. And when they're attractive enough, the two atoms will get as close together as they can, and we call that a chemical bond. Chemical bonds are usually classified as either ionic bonds or covalent bonds. That is overly simplistic because it's more like a continuum where you have covalent bonding characteristics on one end of the continuum, and then you have ionic bonding characteristics on the other end of the continuum, and each compound lies somewhere along this continuum. And where chemists decide to divide it between covalent and ionic is somewhat arbitrary. So you'll actually have some books and chemists saying, oh, that's a covalent compound, and others might be saying, no, it's ionic. So some of them are a little iffy, but for our purposes, we'll try to separate them into these two categories too. All right, so what is the difference between a covalent and an ionic bond? In a covalent bond, the electrons that we think of as forming a bond are shared equally. Okay, just a little picture here. So both atoms involved in the bond want the electrons an equal amount, and so they share equally. We have a branch of a covalent bond called a polar covalent bond, and that's for bonds that are close to being ionic, but they aren't quite ionic. And so the electrons are shared mostly equally, we'll say. So the electrons are a little bit closer, spend a little bit more time to the atom that wants them more. And so it's close to equal, but not quite. And finally, then we have ionic bonding. In an ionic bond, one of the atoms involved wants the electrons, has a much stronger desire, attraction for electrons than the other. And so you can almost think of that atom as stealing the electron from the other atom. So I'm going to write for ionic, the electrons are shared unequally. A lot of people will say they're actually not even shared in an ionic bond, they're donated. All right, so what determines what type of bond you will have? It is a property called the electronegativity, and very simply put, the electronegativity is the attraction an atom has for extra electrons. Attraction for extra electrons, okay? And there are a couple of factors that determine the electronegativity, and we can talk about that later. But the greater the electronegativity difference is between two atoms that are trying to bond, the more polar the bond will be, and therefore the more ionic character it has. So looking down at the bottom of the page here, if I'm going to call E end is going to be electronegativity, okay, En. If the electronegativity of atom A is about equal to the electronegativity of atom B, we'll have a covalent bond. Okay, they both have about the same attraction for electrons, and so they'll share equally. We have the polar covalent around here, okay? And the electronegativity of one atom will be A little bit more than the electronegativity of another one, but not tremendously more. And finally, if we have what we call pure ionic bonding, the electronegativity of one of the atoms, whoopsie daisy, will be a lot larger than the electronegativity of the second atom. And so the bottom line is one of the atoms will want those electrons involved in the chemical bond much greater, much more than the other atom. And so in a lot of cases, the atom with a higher electronegativity will essentially take or steal the electron from the atom with a lower electronegativity. All right, so as a summary then, ionic bonds, which have a large difference in electronegativity, occur between metals and nonmetals, and they involve the transfer of electrons from one atom to another. There's really not much sharing going on in an ionic bond. All right? Why do they occur between metals and nonmetals? Well, you may or may not be aware that metals tend to give up their valence electrons, that means the electrons in the highest energy level, pretty easily. Okay? And nonmetals have a high electronegativity, which means not only do they not want to give up the electrons they have, they would like additional electrons. So it's kind of a match made in heaven. Metals give them up and nonmetals accept them. So any atom that gives up an electron and gives away an electron takes on a positive charge and becomes a cation. Any atom that accepts an extra electron takes on a negative charge and becomes an anion. And then when you have a cation and an anion, obviously there's a very strong electrostatic attraction between the opposite charges. And so you end up getting a 3D kind of conglomerate of cations and anions that are all attracted to each other, and that's what an ionic compound is. And this type of 3D network is what give ionic compounds the properties they have. Think of table salt, for example. They're hard, as you would expect them to be, because the ions are very tightly packed. They make crystalline solid structures. Again, you would expect that because the ions are tightly packed. And so just to kind of look at an overview of what happened, here's sodium, the making of table salt. Sodium is a metal. Chlorine is a nonmetal. Sodium gives up its one valence electron to chlorine, and so sodium becomes the cation, the little blue balls here, and chlorine becomes the anion. On the other hand, covalent bonds, okay, involve the sharing of electrons rather than a transfer, and so they have to be between two metals that have similar electronegativities or similar attraction for extra electrons. Okay, and so covalent bonds occur between two nonmetals. Remember where the nonmetals are located on the periodic table? They're on the right side of, that was kind of a bad abbreviation, wasn't it, of the periodic table. There, I'll just, okay. That's where the nonmetals are. So if you get two of those combining, they have comparable electronegativities. Neither one of them is willing to totally give up a valence electron, so they will share their valence electrons between them, and that is a covalent bond. Now, this is just some terminology that you need to memorize. It's one of those things that might be a trivial multiple choice on your test. When you have a covalent bond and you have two nonmetals, we call that a molecule. Okay? You'll learn in a later slide that when you have an ionically bonded compound, it is not called a molecule, believe it or not. It is called a formula unit, and I'll go over that in another slide, but I just want you to look at both of them here. So just kind of remember that. You can call both of them compounds, but one is a molecular compound and one is a formula unit compound. any type of compound is represented with a chemical formula. Now, I'm sure you've seen those, like H2O, CO2, NaCl. And you need to make sure you know how to read these. I think they're probably pretty clear. The letters represent the element symbols from the periodic table. The subscripts tell you how many atoms of that element shown are present in the compound. So in this case, we have 2 oxygen. In this case, in the bottom, we have 4 chlorine. Okay, so that's pretty easy, I think. All right, so now we're going to talk a little bit about the 2 different types of formulas. We'll actually be doing calculations on these in the next part, or in the last part of chapter 3. But the 2 types of chemical formulas are an empirical formula. An empirical formula is just a mathematically simplified form of the real formula, which is called molecular formula. What the heck am I talking about? It's always best to look at an example. If we have a chemical formula called C4H8, that happens to be butane. You don't need to know that at this point. That's what goes in cigarette lighters. But anyway, so C4H8, you ask yourself, can it be simplified? And I just mean mathematically. So you look at the subscripts, and can they be divided by a common factor? Yes, in fact, they can both be divided by 4. And so therefore the empirical formula for butane is CH2. Pretty simple so far, huh? So, for example, if you have a molecular formula B2H6, you can divide both of the subscripts by 2, and the empirical formula would be BH3. You do have some molecular formulas, for example, carbon tetrachloride, which cannot be mathematically simplified, and so in that case, the empirical formula and the molecular formula are identical. So, in some cases, they will be one and the same. All right, so I'm not really going to talk about these, but in your homework problems and on tests, chemists have a variety of ways that they show a compound. Obviously, you can have its name. You might have the empirical formula, so you've got to be careful what type of formula they tell you they're giving. You can have the molecular formula, which is the real formula. It tells you exactly how many atoms of each element are present. Then you might have what we call a structural formula, where for whatever reason we want you to know something about the shape of a compound, or what elements are bonded to what elements. And so that would be a structural formula. So you can see they tell you if they have single or triple bonds. They tell you which atom is attracted to or is bonded to which other atom. Sometimes if they want you to see 3D geometry rather than using just letters and typeface, they will use what we call ball and stick model. You can see more what the shape looks like. And then more recently, some chemists have said, well, the ball and stick model is not very representative. The space filling models are more representative of what atoms really look like in real life. And so these 2, for example, are considered to be equivalent. All right, so just kind of a flow chart for those visual learners to help us look at some of the difference we've talked about here. So I don't know if you remember from chapter 1, but in chapter 1 we divided matter. We had matter up at the top here. And we said matter could exist as either a pure substance or a mixture. We'll talk about mixtures more later on too. Oh, I can't get my E in there. There. And so we're not talking about mixtures today, but anyway, so this is the branch of pure substances, and we went on to then say pure substances can either be an element, those are all on the periodic table, or it can be a compound, which involves chemical bonds. Well, today I want you to make sure that you understand that elements don't have to be single individual atoms. Elements don't have to exist as isolated atoms. Some elements actually already exist as a molecule. Okay, some elements in our daily lives, in our world, exist in nature already as a molecule. So I'll talk about which one of those do that, but it is possible to have molecules that are in fact elements. Compounds have to have at least 2 different elements to be called a compound. And so we have the molecular compounds. Remember, those are the ones that have covalent bonds. We call those molecules. And we have ionic compounds, which we called the little isolated group here, we called a formula unit. Okay, so that's just kind of a look at the big picture of what we're talking about, all the different species. All right, so this is something you're actually going to have to memorize. The elements that exist in nature, already chemically bonded, so they're in molecular form. All of them are covalently chemically bonded, and so they are called molecules. There are 7 of them. And some teachers give a little mnemonic memory trick. Hofbrinkel, it's just a meaningless word, but it's easy to remember, and it helps you remember all 7 of the diatomic. They're diatomic obviously because of nature. They all exist as twins. They come out in pairs. You will never see one of these on their own naturally. And then the other 2 elements that exist in molecular form already are phosphorus and sulfur. Kind of weird how they choose to exist. All right, so another way to remember the diatomics are, remember there are 7 diatomics. So this is kind of a cool little trick. So if you start at hydrogen, because it's element 1, okay, then you go over to element 7. Remember there are 7 diatomics. And you draw the number 7, you will get all of the diatomics. So that's kind of cool, huh? And then the other molecular elements are tucked right inside of the number 7. So it's just kind of a visual way to remember. All right, so again, a molecular compound is a compound that has covalent bonds. They involve 2 nonmetals, and blah, blah, blah. There's nothing else I really want to talk about here. All right, so again, a summary of ionic compounds. They involve a metal and a nonmetal, which have been, by donating an electron, have become a cation and an anion. And then the cation and anion are held together by the electrostatic attraction between opposite charges. An ionically bonded compound has what we call formula units. So if you were to go into this 3D array, and if you could pull out 1 formula unit from that big thing, NaCl, that would be a formula unit. Okay, right here. Molecules already exist as individual compounds. Like water, if you could go in with small enough tweezers, you could pull out an individual H2O molecule. It's only ionic compounds, because of the really strong electrostatic attraction that exists in this 3D array. All right, so one thing that throws some students off, so it's worth mentioning here, is that you have some ionic compounds, like the 3 I've shown here, and you might get confused if you weren't aware of what they were. So the first thing you will learn to do when you're looking at chemical formulas is you will learn to ask yourself, is there a metal in this formula? And in this case, yes. Hopefully you've printed out your periodic table. If not, you should do that. They all have a metal in them, and you'll see the metals are shown first. Sodium, calcium, and potassium are metals. And so you would be right to say, okay, if I see a metal in a formula, that means it's an ionically bonded compound. That's correct, okay? But then you might look further and say, now wait a minute, it's also supposed to be, a metal supposed to be bonded with a nonmetal, but this has 3 nonmetals in it. What's going on? It turns out that when you have more than 1 anion, well, they make up a single anion, but when the anion has more than 1 element in it, it is called a polyatomic ion. Okay? So NO3, CO3, and ClO are all polyatomic ions. And the polyatomic ions themselves have covalent bonds, because look at NO3, for example. It has a nitrogen in it and an oxygen in it. Nitrogen and oxygen are both nonmetals, so they have a covalent bond between them. But overall, this compound is still ionic because it has a cation and an anion. I hope that didn't confuse you. All right, I kind of already gave you a summary, but so I think you already know the first dash. The second one is very important to know as we start naming compounds and writing formulas ourselves. Keep in mind that the sum of the charges in an ionic compound must be overall 0. So what does that mean? That means the charge of the cations must equal the charge of the anions. Okay? Must be as much positive charge as there is negative charge, so that overall there's no net charge. Okay, and ionic compounds the formula unit always represents the simplest ratio of elements. So you won't ever see, in an ionic compound, you won't ever see a formula that you can simplify like you can in covalent. Okay, yeah, you always already see the simplest ratio of elements. Alrighty, so just a reminder, I think I went over this in Chapter 2, but just a reminder for you. The metals are to the left of the stair step, and metals typically lose electrons to become cations when they undergo a chemical reaction. And so all of these metals will get positive charges or cations. The reasons that I haven't shown the transition metal charges is because they vary. Sometimes the charge is +1, sometimes +2, +3, or +4. So the transition metals are unique. However, the metals are in what we call the A groups, we call those the representative groups, always have the same charge. And so we can just memorize those, and that helps us a lot when we're learning to write formulas and names. So group 1A, always, when they become cations, always get a charge of +1. Group 2A, when they become cations, has a charge of +2. Group 3A, the ones there are of them, get a charge of +3. 4A, that's the carbon group, does not tend to make ionic bonds. They have an equal, well, we'll go over that later. And then it's kind of a mirror image here. You've worked up in charge, and now we're going to kind of approach it from the other direction. So the nitrogen group, now we're in the nonmetals, and they tend to gain electrons, so they become anions. And so the nitrogen group tends to gain 3 electrons and have a charge of -3. You can see what I mean by mirror image. +3, -3 are right next to each other. The oxygen group, when they become ions, have a charge of -2. And I just don't even want this over here. Okay, and the halogens have a charge of -1 when they become ions. So those you should definitely memorize. Okay, you're going to need those. Alrighty. This is just terminology. This is just to remind me to tell you that when you read something that says main group elements, they're talking about the yellow. They're talking about everything but the transition metals. Okay, just so that you know that. All right, as I said before, the transition metal can have variable charge when they become an ion, and because of that, it is trickier to write formulas for ionic compounds that have transition metals. And so just to give you an idea of what you'll be dealing with those, let's say you have a formula FeSO4 and I ask you to name it. You can't just say iron sulfate. We're going to talk about, I haven't even taught you how to name yet, but that would not be correct because the iron is a transition metal, and in some cases it has a +2 charge as a cation, in other cases a +3. And so you have to have the knowledge of what charge the transition metals have because that becomes part of their name. And so I just want you to keep that in mind with transition elements. There are 3 non-transition elements. They're close to the transition metals. They're to the left of the stair step, but they're not smack in the middle, so they're not purely transition metals. But lead, thallium, and tin behave as transition metals. They have variable charges too. So you need to treat them like transition metals. All right, here we go. This is a good time to take a little break if you need one. We're going to start talking about nomenclature now, which simply means naming to chemists. We're going to start with the simplest example. We're talking about ionic compounds now. And if there is no transition metal in the ionic compound and no polyatomic ion, they're quite simple to name, okay? You always name the cation first, and the cation has the same name as the element itself, okay? And then all you do when you go to name the anion, it has a name that sounds pretty much like the element it's made from, except you have to make sure to use a suffix of IDE. So let's look at an example. KCl would be named, K is the metal, remember the metal always goes first, and it has the same name as the element itself, potassium. Chlorine is the anion, so you have to remember in the anion to use the suffix IDE. So instead of chlorine, we say chloride. Same thing, calcium oxide. First you check and you say, okay, calcium is not a transition metal, and I don't have a polyatomic ion in here, so I'm going to name the metal like the element itself, calcium. And I know this is oxygen, but I'm going to change it to oxide because of the rule about the suffix. Not too hard. All right, now let's talk about if we have a transition metal, because that's quite a bit trickier. All right, so because transition metals can have different charges, you need to be able to tell the reader which charge the particular compound has in it. So in addition to naming the cation, like remember we said calcium or potassium, in addition to the name of the cation, you also need to put the charge of the transition metal in the name itself. We do that by using a Roman numeral to show the charge, and we put the Roman numeral in parentheses. So iron, which is a transition metal, as I said before, can have a charge of +2 or +3. If the compound you were talking about was made from iron with a +2 charge, you would start out by naming the compound iron, then you would put parentheses and Roman numeral 2 to stand for the charge. All right, so let's actually do a name. If you see a formula, again, the first thing you should always ask yourself is the metal a transition metal? Is it in the middle of the periodic table? Chromium is, so you're like, uh-oh, now I have to find the charge on this chromium before I name it. How do I do that? The first thing to remember is that the overall charge of any compound, ionic or otherwise, has to equal 0, the overall charge. So whatever the anion total charge is, that must be the same as the cation. And so that's how you figure out the charge on the metal, cation, is you always know what the charge on the anion is, so you kind of back into it. So let's look. A bromine has a charge of what when it becomes an anion? You may need to look back a few slides where I asked you to memorize the charges of the main group elements, the groups that end in A. And if you look at bromine, it's in the halogen group, 7A, and all of those elements, when they become ions, have a charge of -1. There are 3 bromines, so the overall negative charge in this compound is -1 times 3, or -3. Now the cation charge has to equal the anion charge so that there's no net charge overall. So that means the cation charge, the charge in the chromium, must be +3. See, equal to each other, +3, -3. So the name for the chromium in this compound is chromium, parentheses, Roman numeral 3. So we would call that chromium 3 and then bromide. Make sure you understand this page. It can be a little tricky, but it's important. All right, let's now talk about the other thing that can complicate the naming of ionic compounds just a bit. If you have a polyatomic ion, how do you know if you have a polyatomic ion? Well, basically, if you have 3 elements in an ionic compound instead of 2, you have a polyatomic. So look down here at the bottom. You have sodium, you have nitrogen, and you have oxygen. You have 3 elements. So that means you've got a polyatomic. And the polyatomic is NO2. Right? So how are we going to name this? Well, luckily, sodium is not a transition metal, so we're just going to call sodium. We don't have to worry about parentheses and Roman numerals. But since we have a polyatomic ion, we can't go trying to make up some funky name like nitrogen oxygenide something. You have to go to your list of polyatomic ions, which you're ultimately going to have to memorize too. And you have to see that NO2 is called nitrite. And so you just copy that exact name into the name of the entire compound. So NaNA2 is called sodium nitrite. All right, so here's a chart for the polyatomic ions that you will need to have memorized. A lot of students tend to like to put these on note cards with a name on one side and the formula on the other. If I were to ask you the name or the formula of any of these on a quiz or test, you'd have to make sure you have the charges correct also. That's just as important as the name and formula. So you may want to print this out or else make note cards from it. All right, this is just kind of a little quirky one-slide thing, but it's something you're going to need to be aware of. There's a type of compound called a hydrate. It's only a type of ionic compound, not a covalent type. And basically it's a compound that has water molecules actually bonded in with the ionic compound itself. And it's because water is very attracted to ionic compounds. And so some ionic compounds can actually pick water molecules up from the air and incorporate them regularly and rigidly into their crystal structure. So this little dot simply means it's a hydrate, and they are considered a chemical bond, and you have to name them. Magnesium sulfate can exist in the hydrated form and the non-hydrated form, so you need to tell people what form it's in. There are 7 water molecules that are part of the magnesium sulfate hydrate structure, and so you start out by naming it just like you would the ionic compound, which would be magnesium sulfate. SO4, of course, is a polyatomic, and then you would continue to name it. You have to say that it's a hydrate. It has 7 water molecules. The prefix for 7 is hepta. So the entire name is magnesium sulfate heptahydrate. Little tricky, but it's a good thing to know. All right, so we talked about overall the names, but I'm going to give you just kind of a summary list. Always write the name of the cation first. The cation goes first in the formula, also goes first in the name. If the anion is not a polyatomic, if it's just a single element from the periodic table, all you do is make sure you use the suffix IDE. If it's a polyatomic ion as an anion, you need to have those memorized and just use the name of the polyatomic ion. Remember to always ask yourself if the metal in the ionic compound is a transition metal, and if it is, you need to write down its charge using a Roman numeral in parentheses. All right, so do a couple here. I would suggest that you turn off my lecture and then you come back and try to see if you got it right. I'm going to sound like a broken record here, but by far everything I've discovered over the last several years is that problem solving, working problems on your own, and making as many mistakes as you can while you practice is the key to succeeding in chemistry. So even if you completely screw these up and get them wrong, then what you have questions to ask, either of me or a classmate, or try to get them answered yourself. But if you just peek at the answers, you're never going to know the mistakes that you might have made and that can be fixed. All right, I'm hoping you tried these yourself. K2SO4 does not have a transition metal, but it does have a polyatomic ion. So I would start by looking in my polyatomic list and find the name of SO4, which has a name of sulfate. And so the name of this first one is potassium sulfate. The second one also does not have a transition metal, so you don't have to worry about that. But again, it has a polyatomic ion. You can see because you have 3 elements, barium, oxygen, and hydrogen, that tells you there's a polyatomic ion in there. Look up OH, and it has a name of hydroxide. And so the name of this compound is barium hydroxide. Now C, hopefully you caught that iron is a transition metal, and therefore we need to figure out what the charge on the iron in this compound is so that we can incorporate that into the name. So you always start by figuring out the charge on the transition metal by first figuring out the total negative charge in the compound. Chlorine is a halogen in group 7A. Halogens, when they become ions, always have a charge of -1. There are 3 chlorines in this compound, so I need to multiply the -1 charge by 3. So the total negative charge is -3. Because the overall charge of this compound must be 0, my total negative charge is -3. That means my total positive charge must be +3. So that when I add these charges together, I get 0. So it's iron with a +3 charge. So the name of this compound is iron, parentheses, Roman numeral 3, which means that iron has a charge of +3, chloride. Alrighty, so I'm going to work these out for you. Let's see, I'm going to use the blue pen. So potassium sulfide is pretty simple. Potassium is the cation. The symbol for potassium is K. And I will always allow you to use a periodic table on a test as long as it doesn't have writing, your own handwriting on it. And sulfide comes from sulfur. Remember that we put the suffix IDE on, and so we need to write in sulfur. Now, how do we know what the subscripts might be for potassium and sulfur? If you wrote your formula as simply Ks, then you got maybe 50% of it right, so that's a good start. But you have to know the charges of the cation and anion in order to know how many of each you need. So potassium, you may need to look again a few slides ago when I told you the charges of each of the group A elements. Potassium's in group 1, and so when those elements become ions, they have a charge of +1. Sulfur's in the same group as oxygen, and when it becomes an ion, it has a charge of -2. Remember that however many negative charges you have to have the same number of positive charges so that the overall charge of the compound is 0. Well, we don't have enough positive charges. Okay, we need to have a total positive charge of +2. How do we remedy that? We use 2 potassium. So the chemical formula for potassium sulfide, for potassium sulfide is K2S. You can double check yourself, kind of proofread, by checking your charges when you're done to make sure that you've balanced them. Sulfur again has a charge of -2. Potassium, when it's a cation, has a charge of +1, but we have 2 of them, so the total positive charge is +2. +2 -2 balance each other out so that the net charge is 0. Alrighty, let's go on to the second one, calcium hydrogen carbonate. I will tell you right now, kind of as a clue, when the anion name does not end in IDE, that means you have a polyatomic. Remember, every anion from the periodic table ends in IDE, like sulfide, bromide, oxide. So if you have something that doesn't end in IDE, you got a polyatomic. So you're going to need to look on your polyatomic list and see what hydrogen carbonate is. So what it is this with a charge of -1. That is our anion. And notice that when I write the elements involved in, I'm including their charges. That's really important for getting the formula of an ionic compound correct. Calcium is Ca. Again, since this is an ionic compound, I'm going to write its charge It's +2. Now I have to worry about balancing the cation and anion so that the total positive charge equals the total negative charge. I have too many positive charges. How do I do that? I have to add one more hydrogen carbonate. Okay. When I do that, my total negative charge is now -2, which equals the +2, and that's balanced. How do I write this as a condensed chemical formula? That's what subscripts are. So calcium, we only have one of them, so we don't show any subscript. The polyatomic hydrogen carbonate is HCO3. We have two of them, so we're going to put a 2 down here. Notice that when I write the final formula, I do not show the charges because the final formula should be balanced. There should be no net charge, so you don't show any charges. Go ahead and try nickel perchlorate, and I've scribbled so much, I guess I can do it at the top up here. All right, so nickel is a transition metal, and the Roman numeral with a 2 tells us that the charge on nickel in this particular compound is +2. Perchlorate, you should have been able to pick up that that's a polyatomic right away. It does not end in IDE, therefore it's not from the periodic table. It is a polyatomic. And when you look up the formula and charge for perchlorate, it is ClO4 with a -2 charge. Aren't we lucky? I love when that happens. So already, just writing each of these, the positive charge equals the minus charge. We're already balanced, so we don't have to do any extra subscripts. So writing the condensed formula for nickel perchlorate, we have 1 nickel. And whenever we just have one of something, we leave out the subscript. It's understood. And then we have 1 polyatomic, ClO4. So really the only thing we're doing different is we're taking out the charge when we write the condensed formula, and that is nickel 2 perchlorate. That's it. This takes a lot of practice, okay? Even if for some reason it sounds easy to you now, please go to work on your homework, work on the problems in the back of Chapter 3, or I have posted a practice worksheet on our in-class folder and content, but work on a bunch of these, please. All right, so we're coming close to the end of this pre-recorded lecture, and if you haven't noticed already, all we've talked about so far are naming ionic compounds. So now we're going to talk about naming covalent compounds. We saved them to last because they're quite a bit easier. Remember that if a compound is covalently bonded, we call it a molecule instead of a formula unit. And the big difference with molecular compounds is you can have the elements that are nonmetals. Remember, covalent compounds are made from nonmetals. They can combine in different ratios. So, for example, you can have 1 carbon and 1 oxygen. You can have 1 carbon and 2 oxygens. Same thing with nitrogen. Nitrogen and oxygen can combine in all sorts of different ratios. That's not true of ionic compounds. I will not use your time in trying to prove that to you, but every single ionic compound occurs with a set ratio of the elements, and it doesn't change. So sodium and chlorine will always combine in a 1-to-1 ratio. Okay, magnesium and oxygen will always combine in a 1-to-1 ratio. So that's what's different between covalent and ionic. And that this combining in only one ratio has to do with the charges having to balance each other out. So back to covalent compounds. Because they can combine in different ratios, we need to use prefixes in our name to tell us how many of each element are in the compound. Okay, so you do need to memorize these prefixes, 1 through 10. One thing that's the same in naming a covalent compound as it was for ionic is the second part of the name has a suffix of IDE. There are no polyatomics in covalent. Polyatomics are ions. There are no ions in covalent compounds, so you don't have to worry about that. All right, so here's practice. They're pretty simple. I would turn my lecture off and give these a try on your own. So how'd you do? Phosphorus trihydride. Okay. So the rules are pretty similar. The first element in the compound is named just like it is in the periodic table. The second element has a suffix of IDE, just as in ionic. However, the difference between ionic and covalent is we use a prefix to tell the reader how many of the element there are. Since there are 3, we have to use tri. Tri is the prefix for 3. Now you may have noticed or wondered, why is this not called monophosphorus trihydride? Because there's only one phosphorus. Listen carefully to this because this is an important rule. If there's only one of the first element, you leave the prefix out. Okay? If there's only one atom of the first element, you leave the prefix out. Okay, so that's only if there's one of them. If there were 2 of them, you'd still use di. If there were 3, you'd still use tri. Now, kind of tricky again, is if there's only one of the second element, you do use a prefix. Okay? So look at the formula of carbon monoxide. There's only one of the carbon. That means there's no mono. It's not monocarbon. It's understood. However, there's only one of the oxygen, and we do have to use a prefix. So that can get confusing. Dinitrogen trioxide. Okay? If both elements have more than one, both need a prefix. Okay? So most people find covalent compound naming and formula writing much easier than ionic. The biggest problem is when I start mixing formulas of covalent and ionic. When I mix them up, the tendency for everybody is to start using prefixes for ionic and Roman numerals for covalent, and you get all the rules jumbled. So my recommendation is to try to name some ionic and covalent separately, and then do a worksheet where they're all mixed together. And when they are mixed, the very first question you should ask yourself, is there a metal in this formula? If there's a metal in the formula, you need to follow all of the ionic rules. If there's not a metal, you follow all of the covalent rules. All right, so here's going the other way. If you're given the name of a covalent, so your clue, you see any type of prefixes at all, you know you're talking about covalent compounds, okay? Just you have to know your prefixes. So you've got nitrogen, di means you have 2 of them. You have chlorine, hepta means you have 7 of them. Carbon, there's no prefix, which means there's only 1 of them. Chloride, you have tetra means 4. That's kind of a hard prefix to remember. Dihydrogen monoxide, start out with hydrogen, you have 2 of them. Oxide, you have 1. Okay, if there's only 1, you can leave it out. So that's the official name for water, dihydrogen monoxide. Kind of cool. That's it for this pre-recorded lecture. Go practice nomenclature and formula writing, please.